Today we are going to do section 4.5, first order linear equations. Now that just means your differential equation is in this particular form. It has a y prime and a y and everything else x's. Okay, and the x functions can be in front of y prime because all you have to do then is to divide it out. But generally speaking, you just have three things: the y prime, and then some function of x multiplied by y itself, and then equal to some function of x or constant. Okay, a function of x can be just a constant. But anyway, if a differential equation satisfies this formula, then it is a first order linear equation. Now to solve the equation, we use a very neat trick. And what we're going to do is first, we're going to multiply it by a made-up function that we will use to help us solve the equation. And the made-up function is called mu of x. So we'll multiply mu of x to this whole thing here. Okay, so then we have mu of x times y prime plus mu of x p of x times y equal to mu of x q of x. All right, now so far so good. And why are we doing this? We're doing this because we're trying to imitate the function that is, let's see, the product rule. Okay, what does the product rule say? The product rule says if you have f and g of x and you take the derivative, then you have, of course, f prime that equals to something like, now let me line this up perfectly. Now that it be equal to g prime. Okay, what was g again? Oh, g is mu of x. Okay, so we'll write that down carefully. Okay, that equal to g times f prime, okay, plus f times, plus g prime times f. Okay, that is the product rule. Now the reason we write down the product rule is we're trying to make something happen. We're going to construct this thing such that g equals to mu of x, whereas f equals to y, and then g prime is equal to mu x px, and then f corresponds to y because f prime equals to y prime. See, now so we are going to find a mu of x, or let's say we can't find a mu of x that satisfies these conditions, right? Now if we can find such a mu of x such that everything corresponds, that means that this thing is just then correspondingly speaking, g is mu of x, right? So then f is y. Okay, so that means y mu of x, which is fg, the derivative, which is this thing, right, then equals to this side. The derivative is equal to mu of x q of x, because everything match up perfectly. If we can find mu of x, and the reason we want to find it, that means, being that that's the derivative, it means we can integrate both sides. Then y times y mu of x then equal to the integral of mu of x q of x. And at that point, we can solve for y. See, y is this whole thing divided by mu of x, if we can find it. Okay, the trick is to find mu of x, but if we can find it, then we have solved for y. That is, we solved for y in this linear differential equation. So y equal 1 over mu of x integral of mu of x q of x. So as you can see, the mu of x is a neat trick that that help us solve for y, and a neat trick that we use the product rule for. However, then of course at this point the biggest question is, can we find mu of x? Well, let's see if we can find it. Now mu of x, by the way we built it is that mu of x has to be g of x such that mu x px has to be g prime. In other words, if mu of x, so in other words, mu of x is such that if you take the derivative of mu, so mu prime of, or put it this way, d mu of x over dx, okay, which is mu of x is g, so this thing is g prime, so then this is equal to g prime, okay, and so that's mu prime of x, right? It needs to be equal to this thing right here, so that if it does, if we can find something that satisfies this condition, mu x px, if this condition can be satisfied, that is, if we can find mu of x that satisfies this condition, then all this works, and then we can solve for y. So mu of x is a step, okay? And also notice that to solve for mu of x, we only need one solution. If we can find something, anything that satisfies this condition such that this works out, that's all we care about. If we find more than one, we only need one, okay? So we'll search for our one solution of mu of x that satisfies this condition. Now let's look at this condition more carefully. What is that? Well, that is a separable differential equation, right? You have two chunks all neatly broken up. So then we will use the standard trick for solving this kind of problem, which is we do this. We put mu of, okay, we have d mu over here, right, over mu of x down here, and then same thing we did in the previous section, dx on this side and px on this side, correct? No, sorry, we don't need the mu here. So so basically what we're gonna do is d mu over mu equals to dx over p of x, and then we integrate like this, okay, and then that will give us, let me see, sorry, we don't even have to do that. So let's write it some other way, like the way your book does. Now what we're actually going to do is this is mu prime of x equals to let's see, this is actually mu prime of x equal to, okay, right, so let's rewrite this thing too. So we have mu prime of x equals to mu of x p of x. In that case, then we have so we just have this, okay, mu prime over mu equals to p of x, and then we integrate this thing like that. So we integrate this dx. I guess that's similar to what I wrote before maybe, but whatever. The point is we're gonna pull out this integration real quick, which is this is just mu prime of x dx, okay? Well, whatever. The point is then this is a mu. The point is we are going to take out this integrates to become the natural log of mu of x, and that is the integral of p of x dx, and then therefore mu of x is just when you do the exponents, is the exponent of all the stuff, e of integral p of x dx, where the integral is on top of the exponent, which is okay. Now that is, being that we only need one of these things, there are constants in here, but we don't care about the constant because we only need one, okay? We don't care that there's a zillion of them. So this one will be good enough. So we plug that thing, if we plug that thing in our original solution we're looking for, then we will be able to solve for y. And that is all this section is about. So as you can see, to solve this kind of problem, we have to do at least 2 integrations, which sounds like a lot of work, and it is. But sometimes if we get a simple solution, then we can get to the end pretty quickly. Other times you're going to be stuck with a lot of work, right? A lot of work on integration. Now to see an example of that, then let's look at example 4.17, which is on page 413. Now that is, we're going to solve a fairly simple differential equation. So example 4.17, we have a equation that's exactly in the form of the y prime plus pxy equal to qx right here, where we have we just have to identify what is p of x. Well, p of x is let's see. Well, p of x is just 3. Okay, p of x. And then q of x equals to 2x minus 1, then q of x. Then we are going to use this formula to figure out what mu of x is. So after you do some quick integration, and then plug everything into this formula, mu of x, and you multiply and do a potentially much harder integration to get to the answer. However, I guess this is okay as a practice problem. Yeah, I think this thing is sure. So please do this, the rest of it, the grunt work, as part of your homework. Example 4.17 is made easy for you by picking easy numbers. So even though you have to do two integrations, both turns out to be not so bad, because this isn't just an integration. You have to multiply stuff together that makes the integration, potentially make the integration a lot harder. But luckily, that likely won't be a problem, at least for this early example. So having said that, let's look at the next problem. The next example talks about the next example, we're going to skip it because that's not a linear equation. That's just the autonomous equation. If you look at the formula that you're supposed to solve, right? I mean, you have this, look at this. You have dv by dt on one side, okay? The other side just has v and a number. So that's called autonomous. That's not linear. And it fits into the linear equation, but it's not worth doing, let's just say, because we already know how to do that. And also, when if you feel like doing this problem, make sure you don't write down all these numbers, okay, like the book does. Do not do that. That is a complete waste of time. You just write down, say, A for minus, what was it, 11.7096, and then B for 9.8, that sort of thing. Okay, that will make you good. That way you don't have to write down 5 zillion numbers all the time. Okay, so, but we're going to skip this problem because that's just something we've done before. And next, let's look at the next example. The next example, the book decided to talk about electrical circuits, which we are going to skip because electrical circuits take, the book spent 1 page explaining it. Well, trust me, in the physics book, it takes far more than 1 page to talk about the capacitor, the generator, the inductor, and all those terms. So it's better that for that example, all you need to do is focus on the equation, like as in what are we doing here? What you're doing is, if you flip the page to the solution, page 418, here's what you're doing. You are doing this particular problem, okay, which is here's your equation. You need to do the 0.4 I prime plus 5i equals to something sine t, and that's the equation that needs to be solved. Now to solve it, you do exactly the same thing. You identify what is px. Well, px is well, there's a 0.4 in front of I prime, so you divide that out. But anyway, p is some kind of constant. Yeah, p is just a constant. Q is gonna be, okay. Now over here, Q is hard. Q has a sign in it, so it's slightly harder, but still, it's just so you end up integrating the result is you end up integrating something about E and sine right here. And again, do not get blown away by all the numbers. In fact, if possible, please use some kind of a symbol for numbers, like A for 125 or 12.5 or what it is, so that you don't have to write it so much. Anyway, so once you've done that, the integration does come out. So please do that as part of your homework as well. I mean, just this problem, but you can skip the description of physics if you want. And especially if it doesn't seem to make a lot of sense to you. Well, that's because you really need several sections of description to know what all those things mean. But we're math students, okay? We're not physics students. We don't care what it means. We only care about give us the problem, we'll solve it for you. Math problem, and we'll solve it for you. So that's example 4.19. Please simply try to work out the differential equation. Now, the reason I assign examples as homework is because the examples have the exact solution here. And being that we're a video course, then sometimes it's very, very good for you to practice the examples, and then it's there if you need any help, because the instructor can't directly help you. So having said that, that's the end of this section, and I will assign some homework and talk about it in the next video.